physics students. We got our first problem here of the new trimester here. And before we jump into problem 4 in chapter 11, I'm going to talk a little bit about periodic motion. What is periodic motion? Straightforward definition, motion that repeats itself. So, if something's going in a circle around and around, that can be periodic motion. A special kind of periodic motion is simple harmonic motion. And simple harmonic motion is periodic motion where the restoring force is proportional to the distance from the equilibrium position. And we'll talk about that a little more in the problem here. But the force, restoring force has to be proportional to, say, a constant times the distance from equilibrium. And I know what you're thinking, Mr. Kirsten, I've seen something that looks like that before. That's Hooke's law. That's the force a spring exerts. And as it turns out, you're correct. A mass on a spring is simple harmonic motion. So we're going to do a little example here involving simple harmonic motion, problem 4, which states a fisherman's scale, which the fisherman's scale is probably something like a spring, right? And this spring stretches 3.6 centimeters when a mass of 2.7 kilograms is placed on it, right? So I'm going to go ahead and just convert that 3.6 centimeters to meters right away. And we know the mass is 2.7 kilograms. And then the question we need to answer is, what is the spring constant of the fisherman's spring? And the second question is, what would be the amplitude and the frequency of the scale? So in other words, if you took this mass and pulled it down a little bit, I think they said that in the problem that it gets pulled down an extra 2.5 centimeters more, or 0.025 meters. All right. So when I put this mass on, it looks like the scale stretched a bit. Okay. And if I put so I put the mass on, it stretches 3.6 centimeters, and then I pull it down a little more. So what would be the frequency and amplitude of the motion? What would the motion look like? Well, the mass would just kind of go up and down like this, repeating the up and down motion. So it would be periodic. And we're dealing with Hooke's law here for springs, where the restoring force is proportional to kx, where k is our spring constant. So indeed we have simple harmonic motion here. Okay, so part A of the problem asks us to solve for the spring stiffness constant. Well, let's go back and do a little free body diagram here. We have the force of the spring and we have the weight here pulling down. So two forces that are equaling out. So the force of the spring would be kx, and that would have to equal the weight of this mass, so that would be mg. So if we wanted to solve for the spring constant, we would just do mg divided by x. So plugging in our numbers here, we would do 2.7 times 9.8 divided by x, the distance stretched, which would be 0.036. Notice we have all kilograms, meters, and meters per second squared here. And if we punch that into a calculator, we get about 735 newtons per meter would be our spring constant there, right? Why is it newtons per meter? Well, this is a kilogram. This is meters per second squared. A kilogram meter per second squared is a newton, and this is in meters, so that would be our spring constant there. So part B says, what would be the period and, the frequency and amplitude of the oscillation? Well, let me show you an equation here on your equation sheet. It is the period of a spring. All right, if you have a mass on a spring, the period is given by this equation here. So the period or the time for one oscillation, t is defined to be period, and it's measured in seconds, and that's the time for one complete oscillation. So the period of a mass on a spring is, there's an equation that says it's equal to 2 pi times the square root of m over k. Now, where did this equation come from? The derivation's a little lengthy, but it's in section 11.1 if you want to read through it. So let's figure out what the period is. In other words, how long would it take for this mass to go down and back up and back, right? One complete cycle, right? That would be equal to 2 pi times the square root of the mass, 2.7, divided by the spring constant, 735. So if we plug that into our calculator, we would get a number. What number would we get here? We would get 0.38 seconds would be the period. So that's how long it would take for one oscillation to take place, right? One full down and back, one complete cycle. Well, how many cycles would there be every second? To get to that, we can use this little relationship here. The period is equal to 1 over the frequency. Let's see if we can figure out what that means. So frequency is 1 over the period, or 1 over 0.38. And that turns out to be a number, 2.63, 1 over seconds. Okay, let's talk units here. 1 over seconds, or sometimes written inverse seconds, is defined to be a hertz. All right, sometimes called a cycle per second. All right, so the frequency of this guy's oscillation is 2.63 hertz. This means every second this guy would go down and up 2.63 times. So there would be 2.63 cycles per second. All right, we're almost done here. Last thing here, we need to know what is the amplitude. Amplitude. Okay, so let's do a quick graph here where we put time on this axis and x position on this axis. So what did we do? We pulled this guy down an extra 2.5 centimeters. What would its graph look like? Oh, it'd look like this, a nice sinusoidal wave, or maybe this is a negative cosine or something, right? What is the amplitude defined to be? Well, that's this guy right here, right? The that would be amplitude. All right. So the maximum displacement from equilibrium is defined to be the amplitude. And in this case, the amplitude would just be our 2.5 centimeters, because that's the distance we displace the spring from the equilibrium position after we put the mass on. Okay. So there we go. There is problem 4. Which talks about the period, the time for one oscillation, the frequency, the number of oscillations per second, the amplitude, the maximum displacement from equilibrium, and our spring constant. So hope that helps clear up some things for you. Nice work, AP Physics students.